Okay, here we are, ready to start the fourth and probably last screencast of the review, discussing the sample questions for physics midterms 2012. This first question is unsportsmanlike, but I want you to remember that on any test you get from me, there's basically three categories of questions. There's very easy. There's moderately difficult. And then there's really hard ones to give the real overachievers something to do. This is why, you know, if you come out of a test with a raw score of 66%, raw, you did awesome. And we turn that into a good grade. But when you're looking at one of our tests, and this is generally what you should expect in college as well, be aware, some of the questions are supposed to be very easy. Some of them are supposed to be very hard. Your trick in doing your triage at the beginning of the test is to try to identify these and make sure you nail them. Careful, because they're sometimes confused with these. So this one's going to be hard to mess up unless I'm much more fiendish than I remember myself being. This test, and I apologize for our viewers at home who've heard this part before, there's going to be multiple choices in the traditional form, 5 choices, A through E. And we've been working together long enough to know that, for you to know that the last one is usually something annoying, like not enough information, or more than one of these, etc. So whenever you're doing one of these tests, you are going to annotate your copy of the test. You're going to make all kinds of drawings on your scratch paper. And don't lose points because you didn't keep track of how many were correct or something. So if you are faced with let's see, what's something you're not? What's a unit of measurement not commonly used in physics? That is certainly, you've been yelled at enough for using inches instead of centimeters. So that would be a good, this is not. I'm going to mark that to myself. That is a potential answer to this question. And if maybe down here there's slugs, that also is not. Maybe this is meters, maybe this is meters per second squared. Careful with these double negatives, all right? Because this is, that's okay. So it's not a response to this question. This is, so it's not a response to this question. You with me? So there are 2 things here that are not a unit, so the answer is more than 1 if that's what's available. Every time you make a mark on the paper, you're reducing the active cognitive load of your mind. Nothing on this test is difficult. It's not difficult to toss a tennis ball up and down, but it takes more practice to toss 3 of them up and down at once. Any uncertainty about this stuff? Good. 2 observers in 2 different trains disagree when describing the motion of a car they can both see. Which statement is true about this situation? Okay, there's no choices here. So can you please brainstorm at your table a couple of statements that would be true and a couple that would not be?
looked at it, I was like, hi. That's a good start, right?
Okay, throw something out here that we can put into either column. Try to be like, you know, you guys, be fiendish like me. I know you can do it. What would I put up here that would be really tempting, but not true?
The car's moving backward.
Oh, hey, that's great. You've been paying attention to my tests. That is not necessarily true.
The car is moving.
The car is, well, moving according to who?
Because if the person could be moving, the car could be moving.
Hang on, let's stop review. How do we tell if something's moving? What's that?
If it advances.
Yes, even easier. The cartoon version, the scope test. Can't go wrong with the scope test. To use the scope test, you need to designate an observer. So an observer in A, his scope's telling him one thing about the car. Maybe the car is getting closer or getting bigger in his scope. So he says, yo, the car's going this way. And maybe the observer in train B is swinging his scope this way as he follows the car. And he says, oh, the car's going that way. Or maybe, actually, if they're both pointing that way, do they disagree? No. Okay. What if one observer sees the car moving with a constant velocity and the other says it's not moving at all? Okay. So I suppose A and B differently what? With but it's not their motion that matters, is it? It's their direction. Just look, whatever ends up there in the end, the road to happiness is to use the scope test. Now, if there's a choice like this, let's the car is at rest with respect to the ground. Remember the way you judge these things. Don't look for a reason to think that this must be true. Try to show that it's not. And do that with all of the answers that you are offered to choose from. If you go looking for a reason to believe it, you will always find it. That's the way the brain works. Instead, try to find a counterexample where the car could be at rest with respect to the ground, and A and B will still disagree about its motion. That should be easy to come up with. Any more questions about this? Which of the following statements is correct about the interaction known as friction? What's everything that we know is correct about friction? Let's see. Make a list.
It is not a force.
That's going to be a really tempting thing for people to put on their list. Is friction a force? A force is a push or a pull between two physical objects. Is friction something pushing or pulling on something else?
It's kind of there.
Well, like a lot of things that aren't forces, like the force of the throw, people would say, well, there's the force of the throw on the object that you threw up in the air. And you say, no, that's not a force, because a throw is not an object. And they'd say, well, the force of your hand then. And you'd say, your hand isn't exerting a force if it's not touching. So, if you shove something across the floor, and it slows down and stops when you let go, can you identify an object that exerted that force? Yes, the floor. So, it's perfectly reasonable to be confused and say it's not a force, because because all our talking about the F word was the force of something on something. Friction is a force, but it's confusing, because we use the word friction as a shortcut for the force exerted by two surfaces on one another when they're moving or when you're trying to make them move. It's the horizontal part of the force between two objects. And it's really not horizontal. There's a fuller definition. The force parallel to the surfaces in contact. How about this? Force of friction can never be zero. Correct or incorrect?
I mean, incorrect. Oh, no, incorrect.
Yeah, this is incorrect. Think of a counterexample. Yeah, that chair, there's clearly no force of friction between the floor and the chair now. How about something very similar? Is the force of friction zero if the object is not moving? Let's see. In other words, can V be greater than zero if wait. Sorry, I messed up. Can velocity, if force of friction is greater than nothing, can the, no, never mind. I've managed to confuse myself. Trying not to give away too much of the fun, but can friction be non-zero for an object that's not moving?
Yes.
Yes, you can have force of friction greater than 0 for an object that is not moving. Yep. Oh yeah, that would be cool.
Yeah, because I remember.
Yeah, that was helpful. Okay, good. Make an example of your table. Just do something where you can identify a force of friction that's greater than 0, even though the object isn't moving. Can we use that? Can we use that waste paper basket standing in the middle of the floor? No, that doesn't qualify. All right. Jen, just shove on that table you're leaning on, please. Just give it a shove. Not hard enough to move it. You're pushing? Okay. Exert a force, but not enough to make it. Okay. I can see you're pushing, but the table's not accelerating. So the force of friction is balancing the force that you guys exert on it, and yet it's not moving. Let's see if we can reconstruct that graph that you guys... We invented that together, you know, as far as I know. And I think that's really super. What did we do? We had... What did we have on which axis for friction? We had... That's right, we had the force of... We had the total force on the object. And then we had force of friction on object. And this was interesting. Let's make a object. Unbalanced force. And when the unbalanced force was 0, like on that waste paper basket right now, the force of friction was 0. For a while, when we pushed on the object, the force of friction increased as well. Until a certain point. And after a certain point, yes, we found that. Here, actually, I improved it. That's one graph. Here's two different experiments. What's the difference? Same object, two different experiments. Yes, gosh, that's awesome. And this and the blue line?
They started registering like this or making accounts right after it was already.
Yes. So when the object is not moving, or to be specific, the two surfaces are not moving past each other, the atoms and molecules have had time to make friends with the atoms and molecules in the other surface. We call that static friction. Static as in not moving. And that gets greater and greater up to a certain point, at which point the object begins to move and static friction no longer exists. This is the maximum force of static friction. And that's a characteristic of the two surfaces and how hard they're pressed together. You're not likely to have to calculate that. But the formula is in the review materials if you're concerned. Once the object is moving, it's like passing your friends in the hall. You don't have time to get friendly. So the force of kinetic friction is constant as long as the object is in motion. And since we're doing so great here, let's review the index quantities for concerning friction. These are characteristic of the two materials in characteristic of the two materials in contact. Mu sub S is defined as the maximum force of static friction. How hard you can push until the object just begins to move.
Wait, what's that mean?
This is a mu.
Wait, what is it?
This relates the maximum force of static friction to the perpendicular force between the surfaces. No. Because you don't need to know it because it's always on a formula sheet. But you should recognize what it is.
How do we use it?
How do you use this is the question. Well, anytime we have a relationship among quantities, you can use this to, in the best case, reason about the physical world around you and derive more truth and beauty from the world. In the worst case, you can use it to solve a problem or answer a question. And a relationship among any three quantities is typically used in school settings where you know or can figure out two of the quantities and you're asked to find the third. Or if there's n quantities in the relationship, you know n minus 1 and you're expected to find the nth. Just remember, this is elementary. The same relationship can be expressed in three different ways. Kelly.
Parallel on a surface on surface, that's when the object is moving.
Since this is static friction, that's standing still.
Okay, but what instance would that be?
Well, let's see. If I'm standing here on the floor, or if I'm pushing the table across the floor, which is all you'll be getting in introductory physics. Or the ever-popular crate, 100 kilograms. What's the perpendicular force of the surface on the crate? Force diagram, crate. Got the earth pulling down. What's balancing the force of the earth? Force of the surface.
Will we get a quantity?
If necessary.
Is the force, what is, if it was numbers, and you're given numbers?
For this example,
Is it
if you're pushing the perpendicular force of the surface on the crate, in this example, is equal to the force of the surface on the crate, and that's equal to the force of the earth on the crate.
So, would it be the positive value or negative value?
Okay, to be more strict, this is the magnitude, so the amount.
Absolute value. So positive. Okay. That makes sense. But we're not given this on the test, are we?
You're not going to have to do calculations with this.
Okay. But we have to know that concept.
You see this on your formula sheet. You should be able to identify what these quantities are and reason with that if necessary. Yeah. Yeah, wait, no, sorry, Jen.
Yeah. Is it only static friction for the beginning? Because then it starts moving, but you're saying it's still static friction.
This is
No, for the red.
the red. Okay. The red is an the red line shows when the object is not moving. So the unbalanced force is greater and greater up to a certain point where it stops moving, and then there is no static friction anymore.
Like I'm pushing you, but you're not moving it, right? And then until I move you, it starts going flat again.
Yes, this is confusing. Yes.
I kind of missed what you said before friction. Is there any way you can about this? I think it was the next question. Or was the question back?
I think this is the first thing we started talking about here. Dan.
Oh, you weren't talking about anything before that, though?
I'm lost now. See if you get.
Okay, never mind. I'm good.
Okay. If you think of something, let me know. Dan? So what's not going to be true about friction?
Can't be zero. Well, the force is can't be zero.
Force of friction cannot be zero? Well, it is for that trash can there, right? If there was a sideways force between those two between the bottom of the trash can and the floor, we'd see it accelerate, presumably. How about statements like, sometimes friction can be ignored? Huh. That's a true statement. Friction depends on the surfaces in contact. Friction depends on only one of the surfaces in contact. Is that a true statement? No, because an ice skate's very different on ice than it is on carpet. Okay. This is easy. Now there's some questions like this on the exam too. Compare quantities. And there's a couple different situations where circumstance is described and then you're given a list of quantities to compare. So this probably looks familiar. A snowball moving west at number not given. Let's make something up. Collides with and sticks to the windshield of a car driving east at. Let's make something up. Compare the quantities described below for this situation. Okay, what sort of questions would I ask you about this? Let's list some physical quantities. Velocity, delta V. There are quantities that are force. Yeah, we could totally ask about a change in momentum. Yeah, totally.
Is it the change? No. forgot.
Yep.
Did you say that the change in velocity is not
Just didn't hear you.
Did you say that the change in velocity is not acceleration in physics?
Change in velocity is how much your velocity changed.
Yeah.
Okay. Acceleration is the rate at which it's changing over time. So change in velocity is to acceleration as change in position is to velocity.
Yeah. But, so they're in the same direction.
They're in the same direction.
Then why do we have two different statements?
Yes, strictly speaking, they are different quantities. Let it slide for now. You're not misunderstanding anything.
Oh, okay.
Okay, you're not misunderstanding anything. There's a distinction which you are working on discovering. Don't worry about it for now. Let's see. What if column A is all about the snowball and column B is all about the car? Which has a greater delta V? Okay. Yeah. Write all this out. Make a sketch. Take the information they give you, they being me. You have an initial state. Car, snowball. In this case, the snowball is traveling faster than the car. And you have a final state. And you can use your real-world knowledge. How much is the velocity of the car changed? Probably not much. So do a delta V for the car. Practically nothing. Do delta V for the snowball. And you're ready to compare those if necessary, yeah? Delta V for the car is the difference between this and this. Delta V for the snowball is the difference between this and this. Let's see. How about F's? If you're asked to compare force of car on snowball with force of snowball on car. Okay. Whenever you see force of A on B, anything that resembles force of A on B and force of B on A, okay? This sets alarm bells ringing in your mind. Yep. Okay. Remember Newton's third law. And remember, for every question, there's at least one obvious, clear answer, consistent with common sense, which is completely wrong. Moving on. This chart, now we've got some momentum bar charts, some constant momentum bar charts to match. Sketch a chart right now that could match this scenario. We've got two objects, so there must be A and B, and the change is 0, like I said. Sketchez-vous. Whoa, time flies.
No, it does.
5 minutes left.
Oh, look, I'm doing all the math. There's a countdown right there.
Okay. Here's the long form. Initial momentum of A, initial momentum of B, final momentum of A, final momentum of B. Okay. Now let's start with the really obvious. Two bars that are the same size in the initial state. That's really obvious, right? Those are not moving with the same speed, necessarily. Not. Why not? Because this is momentum. No is velocity. Two objects can have the same momentum without having the same speed or velocity.
Wait, can you explain that?
The question asks, does this chart show an initial state in which two objects must be moving with the same speed? Since we don't have any information about the mass of the two objects,
Right, then they're not.
okay. So in fact, lacking information about mass, is there any chart that would qualify?
If they're the same.
Oh, 0.
Oh, ooh, fiendish. Oh, that would be really rotten if I did that. But I suppose in principle, it would be legit to say that those are two objects with the same speed. That would be bad. Well, not moving is a speed of 0. That's a legit quantity. Let's see. Oh, next slide. Total momentum changes from initial to final state. How do you know? You add this up. Does A plus B initial equal A plus B final? That's constant momentum. That's constant anything. Total initial equals total final. Two skaters who roll toward each other and then push away. Let's see. Let's do some partials. Could this match? Could this match? Could... No, that's the same thing. So, opposite directions has to mean opposite direction. Opposite directions of velocity has to mean opposite directions of momentum. So this is okay. That could be. This could not be. Same direction of momentum. Now let's see. If they push away, they're going to be going in the opposite direction afterwards. So an after state like that, legit or not? Not good. Does not match because this is the same direction as this. So although the initial part matches on this chart, the final doesn't. All this is on mophysics.com. You have my email and cell phone, and you can see me next week. You can come in after school, come in for physics lounge at lunch. Have a good day. Here is the end of part 4.